Now we want to focus on a particular parallel application, one that simulates ocean currents. This is important in climate modeling, and we'll be considering it for the rest of today and also the next class. The motion of particles in the ocean depend upon atmospheric forces, friction with the ocean floor, and friction with the ocean walls. So we can represent the ocean as a grid. Now, of course, it's a big ocean, and we don't have an unlimited amount of memory to devote to it. So we'll only be able to sample these quantities of friction, ocean temperature, etc. at particular points in the grid. The problem is continuous in both space and time, and we're using a discrete approximation to represent pressure, velocity, and currents. The model uses a set of 2D cross-sections throughout the ocean basin and solves equations of motion at all the grid points in one time step. And at each time step then it updates the state of variables, and then it goes back and does the next time step unless it's converged. So we have to test for convergence, and if not, we go back to do the next step. The tasks in this simulation are arbitrarily defined portions of work. In this example, it's probably something like calculations on a single grid point. Yeah, that's probably too small. Maybe a row of grid points or any arbitrary subset of the grid. Tasks are chosen to represent some natural granularity in the work. If it's a small granularity, we have a fine-grained decomposition. If it's a large unit of work, we have a coarse-grained decomposition. Now the threads are what are actually going to be used to cooperate during the execution of the simulation. So we need to group the tasks into threads. Each thread is going to be assigned to a processor. We might have more tasks than we have processors, and that just means they can't all run at the same time. They might be different length, and so two tasks could run on one processor while one task is running on another, or something like that. As long as the load can be balanced sufficiently, we don't need to have the threads correspond one-to-one with processors. In the ocean simulation, though, we might have threads that correspond to one-to-one with processors because we could divide the grid into portions such that each thread size portion has an equal number of rows. So let's say we have, 10,000 rows and 16 processors. Well, then we wanted to assign 10,000 divided by 16 rows to each processor, right? Okay, so we've got 4 steps in parallelizing a program: decomposition of the computation into tasks, assignment of the tasks to threads, and this is task creation in Solihin's terminology, and he also included deciding which variables are local there, just through scope analysis of variables. That was really part of the decomposition. Then there are 2 other tasks that constitute mapping. First of all, orchestration of data access, communication, and synchronization among threads. And then finally, mapping the threads to processors. So you see a diagram of that below. You take your sequential composition or computation, and then you divide it into tasks. So there are a lot of tasks. You group the tasks into not so many processes, and then you decide how the processes communicate. They become a parallel program. Then you decide which processors each process executes on, and then you've got mapping. That gives you the parallel execution of the program. So you start out by partitioning the tasks into various processors, and then you orchestrate the threads into a parallel program and then assign them to processors. Notice the difference between the stages of decomposition and assignment, which are mostly not architecture dependent. You're just looking for parallel work in the program. So you could parallelize it that way pretty much for any architecture. And then orchestration and mapping do tend to be architecture dependent, because you have to get the threads communicating with each other. That means you need to know how efficient it is to use various communication primitives. And with mapping, you also need to be aware of the topology of the multiprocessor so you get the data close to the processes that are referring to it.